is back on. Recording is back on. So let's take a look at another example. Again, we're gonna follow these 4 steps. And once we're following those 4 steps, we will automatically getting all the components that are needed in order to carry out the kinematic analysis. This is a bit more involving, this example, and it's a bit more involving because we have more bodies. But it's not changing the big picture at all. The big picture always remaining the same. Even if we were dealing with, say, 10,000 bodies, still the big picture is with no changes whatsoever. And that, again, is a beauty of this method. No thinking, no need to find a relation between this and that. You're just following the certain steps and you automatically get what you need. Okay? So, number 1. So we need Jacobian matrix. In order to have a Jacobian matrix, we have to have the constraints. How is that we can express the constraints? Well, with help of the equation that we are very much familiar with. R plus rotation matrix multiplied by vector U bar. By the way, it will be all right to make a tattoo regarding that equation because it's not going to change. We're going to keep on repeating that forever. So it will be kind of, I would say, that good investment if you make tattoo of that equation. All right, so we're going to follow that. With help of that equation, we're going to be able to express the Jacobian matrix that we need in order to compare the the Newton difference. And once we have a Newton difference, then we can solve the position level analysis, or we could to go the velocity level. And then acceleration finally. So let's take a look. But before taking a look at this, I'm not sure if this is a good time to do this, because I would like to follow this carefully, but still I'm thinking that, okay, let's go through this example, and then I have one in-class quiz, which is related to kinematic analysis. Okay, but let's do this first. So first step, here we are. So the first step is this, Jacobian matrix. Now this time I'm going to take a little bit of shortcut because this is a system we looked already 2 weeks back. And at that time we were able to express 5 constraint equations that were related to, first of all, revolutoid that is located in that corner, and it is constraining the first body that is called body A, and then revolutoid that is coupling. Oh, hold on. Oh no, you saw that in class quiz already. So it's, but we'll get back to that. So don't think about it this time, because I would like you to put your full attention to this example. I'm gonna give a good hint to you, really good ones. First one is this: particle don't rotate. Okay, so we were here. Okay, so then there is a revolutoid that connects 2 bodies together, and finally I have primitive joint plus driven constraint in a location Q. Okay, how many constraints I have in total? 6. How many generalized coordinates I have in a system that consists of 2 bodies? 6. You all voting for 6? You're all doing like this. Are you 100% sure about that? Yes. Good, because it's 6. It's 6 generalized coordinates that are needed in a system that consists of 2 bodies. 9 generalized coordinates are the system that consists of 3 bodies, so on and so forth. All right. Now, we have all these, well, we have already these 5 constraints. The one remaining constraint is associated with that driven constraint. And now the driven constraint, look at this. So this is important. So I'm constraining the motion in along the global y-axis. That's why I have here this driven equation that is placed in a position where the x position is expressed. Y position is equal to 0 because the system is not allowed to move along the global y direction at this point Q. This motion is not allowed. Clear. All right. So that's gonna give me sixth constraint equation. First 5 are expressed here, and my sixth is the one that is shown here. How is my vector of generalized coordinates? That consists of 6 components, but what are those 6 components? Obviously, the first 3 ones are associated to the first body, remaining 3 are associated to second body. So, the first one is translation of first body in a x direction, translation of second body in a y direction, angle theta, and then the same for body B, which is the second body. Now I'm gonna just go ahead and take a full use of a symbolic math tool. I'm gonna introduce these components to my math tool. I'm gonna ask this to compute to me Jacobian matrix. Jacobian matrix will have the dimension of 6 times 6. 6 rows because of 6 constraint equations, 6 columns because of the 6 generalized coordinate. Clear? All right. So then, excuse me. Then, it's not showing here how to, this is not showing how to compute that. I'm obviously missing one slide here because, the delta Q, the Newton difference computing is missing here. But it's quite straightforward because you need this one here, and then you multiply, you take a universe of the Jacobian matrix, you multiply that with the constraint equations. That's how it goes. Sorry that I missed that one slide. Let me take a look at it, and if I'm able to find it, I'm going to add that to my presentation. But I'm going to move on directly to step number 3, which is velocity analysis. So here I have all my constraint equations, 6 components in total, a total of 6 components. Now I'm going to differentiate those with respect to time. Take a look at this. The only component where the time is mentioned is this one. So when I differentiate that with respect to time, it's going to give me this vector. And by velocity, I can get by inverting my Jacobian matrix, which is this one here, multiplied by this one here. And it's about substitution. Nothing but the substitution. The final one is a painful one. I need to take my Jacobian matrix. Then I'm going to then Jacobian matrix will be multiplied by velocity of generalized coordinates. It will give me a vector of 6 components. This vector will be differentiated with respect to generalized coordinates. It's going to give me the matrix where the dimension will be 6 times 6. And that finally will be, this is how the 6 times 6 matrix look like. That finally will be multiplied by velocity of generalized coordinates. That's going to be, the one component that I needed here. And then when I differentiate the constraint equation twice with respect to time, that's how it reacts. Again, Jacobian matrix itself is not the function of time, so that's why this component is equal to C. So then I'm ready to solve the response. You ready to see something amazing? Let me repeat, something amazing, amazing. Where is it now? Here. Ready? I hear whispering. Okay, you ready? Yes, you're not dreaming. This is real life. Unbelievable. Look at that. So we did it. Group hug. No? Okay, so let's just continue. But, big step in your life. Big step. Okay, so we are now able to solve the kinematics. And now what we did, so of course, this looked ridiculous because the animation is ridiculous. It's just, two bodies are moving like that. And now when you go back to your home and you're very proud of yourself, and you're explaining that to your mom and dad, and you're showing this animation, they will be like, oh, please. Because they don't understand the big picture behind what we do. We know that now we can apply this knowledge to whatever mechanism we want. And once we have this knowledge, then it will be just the small steps for us to start looking at the dynamics. That's what we're going to do next. All right. So let's go and check it out, this in-class quiz. And let me advise you before you're entering, don't enter your answer. Don't enter your answer because I would like to, so it's not on yet. Okay, that's good. That's good. So let me put it on. So the next, and let me show what is the next in-class quiz. So is this one. Kinematic analysis can be carried out if you know several of the bodies. You cannot say that in loud, but moments imposed to the system, forces imposed to the system, constraints of the system. So what is an information you have to have in order to carry out the kinematic analysis? This is not a trick question. This is not like I wanted you to feel confused. This is very straightforward. Think about what's the role of kinematics and how the kinematics reacts against forces and moments. This is important to understand. How is the relation of kinematics to forces and moments? And then what are really the information we need? Now you guys are very confused and not sure which is a correct answer. I can see that it's not going to happen. Today is not going to be today we're scoring 100%. It's not going to happen. Would you like to think about this a little while? But please remember, what is the role of forces and moments in kinematic analysis? Okay, so if not sure, go and consult with your fellow student. But please remember this. It's very well possible that your fellow student have no idea, absolutely no idea what this is about. But consult, discuss, make a negotiation, because maybe you can converge to solution that is correct. Okay. Let's take a look how the Socrative look like. So we have 60 answers already, and I think we need some more to close this case. 7. Last time we got, what was the number last time? What was 80? 81. 81. So maybe, so soon we're going to be in 81. This is a problem because the online participants, they're coming a bit behind of us. So they don't have that much time to react to these questions that we do. But now we have 82, 84. So we're missing like 9 students. So can we close this thing? Okay, so it's almost there. So it's only 6 students. Success rate, 100%. 100%. 100%. Who is with me with 100%? I'm the only one. Come on, come on. So can-do attitude. This is supposed to be a team effort. 66 is very low. So if it's going to be 66, we're going to close for today. Okay, so let's take a look. Oh, please, it was this close. This close. I have some very good news here. Very good news. Shape of the body is not the one that you have to have in order to carry out the kinematic analysis. Very good, because this was the only one that was a bit difficult. Because the vector u bar is associated to cell of the body, but that's not enough information to carry out the kinematic analysis. How much forces and moments have to do with the kinematics? Zero. Same thing like how much particle can rotate. Same category. So it's not about the forces, it's not about the moments. I know that is a bit confusing because later, as a post-processing procedure, it is possible to plot it out the forces and moments, but that's a bit different story. They are not in a play when you carry out the kinematic analysis. Okay, so let's moving on. And now comes something that it's going to be that part that I promised that is going to be painful. Prior to that, we're going to take a look at a little bit about what's the value of kinematic analysis. Now let me explain you one example where the kinematic analysis is used. This is a study that is related to bicycle dynamics. Now, in order to carry out bicycle analysis, or in order to create the equation of motion for bicycle, we need to take a look at how many degrees of freedom the bicycle have. And this, by the way, is an interesting study, the dynamics of bicycle, because it's not clear what makes bicycle to be stable. It's not at all clear. There are, some stories that is about the gyroscopic forces that is making it to be stable. And then there's stories that is a little bit about the steering kinematics that makes it to be stable. And then, this and that makes bicycle to be stable. But the bicycle is a kind of the machine that is self-stable. You can push bicycle to go forward, and it goes forward. And then you can run with your bicycle, and you can push it sideways in a transverse direction, and it will start vibrating, but it will stable. This vibration will damp down. And that's because of the dynamic properties of the bicycle. And it's quite surprising how it behaves. Now, in order to demonstrate something that is called virtual sensor technology, we made an instrumentation of bicycle. And the bicycle instrumentation is such that we are measuring 3 degrees of freedom that the bicycle model have. And these 3 degrees of freedom is the steering angle, leaning angle, like this, and forward velocity. This, by the way, is a system that consists of non-holonomic constraints. And then we are measuring those degrees of freedom. Once we are measuring those degrees of freedom, then we are using these measurements as additional constraints that are fed into to model. And once we're running the kinematic analysis, we can get the understanding about the full state of the bicycle. And that's something that is quite interesting, because that full state of the bicycle can be later used in order to make an interpretation and estimation about the forces, which is not the part of the kinematic analysis, but as a post-processing procedure, we could get the estimation about the forces. And that's exactly what the virtual sensor technology is about. So let me repeat it. So we're measuring the quantities that are easy to measure, which is steering angle, leaning angle, and forward velocity. This information comes into model. Model is using kinematic analysis to get the full picture about the bicycle state. And using some pre-processing procedures, it is making estimation about forces that are imposed to bicycle. So input is a simple measurement. Output is a forces that are very difficult to measure. This is a thing we're doing together with my good friend of Arjen Schwab. Arjen Schwab has been in the business of bicycle dynamics already forever. And not long ago, he made a study about bicycle dynamics. And this is interesting. So he was able to publish his study in a science journal. And if you want to take a look at that, it's available. The details of the paper is mentioned here. And the title of the paper is as follows: A bicycle can be self-stable without gyroscoping and castering effects. So it's interesting paper. It's all about the bicycle dynamics. So this is where we can apply our knowledge as well. Not quite yet, because we're missing one important component. And one important component is the dynamics. That's what we need to look next. But this study here too, a lot of role is in the kinematics. Okay, so let's take a look how this is. So how it reads. So bicycle is riding, someone is riding the bicycle and we're measuring these quantities, and this is the full state of the bicycle. So we're just, plotting out the different angles, different generalized coordinates. And so we're gonna stop the simulation, we start plotting the forces. Estimation about how much force is in both the front tire, rear tire, different parts of the bicycle. That's called virtual sensor technology. For your information this time. Something that is good to know. Okay, and now I know that this is kind of slow, that it's not looking very good. The visualization is equally bad that in my case of kinematics, but the idea is interesting. And now we're going to stop the simulation, and the next we're going to start plotting out the forces that are imposed to the bicycle. Again, technology is called virtual sensor technology, model-based sensoring technology. Okay, so with that, so we have 25 minutes to time, and we really need to open the dynamics. So this will be that painful time of the course. The most cumbersome time of the course, most mathematically involving time, but we're gonna make it happen. You ready? No, but still we're gonna make it happen. Okay? By the way, any questions or comments so far? It's like everything is clear or none of this stuff makes any sense. Or somewhere between. Maybe somewhere between. Okay, so we're gonna take a look at the concept of virtual work and virtual displacement. This is where I would like you to have full attention what I'm about to tell you. Because otherwise, you're gonna miss a good part of the course. Okay, so breathe really deeply. One more time. Do you have can-do attitude? You have? Okay, so we're good to go. So let's look at what is this virtual displacement and virtual work. And now we're going to change completely the point of view, because so far, no discussion about the forces. And from this point on, it's all about forces. All about forces. We have a great challenge. We have a big challenge in our head. And this is a challenge that, everything has to be expressed in terms of variables we are dealing with. And this is, something that is very important to understand. So we have to express everything in terms of variables that are expressing the system. All right, in a multi-body system dynamics, what are the variables called? Generalized coordinates. So we have a set of coordinates that is called generalized coordinates. And what we need to do here is that we have to express all the forces. And by the way, we only kind of have two kind of forces. We have externally applied forces and inertial forces. And we have to express those forces in terms of generalized coordinates. That's what we have to do. So let's look at the situation. I have here a potato-shaped body, and the potato-shaped body is just a one-body planar case. How many generalized coordinates I have in this system? Now you're very is it that it's becoming late, or you just don't want to communicate with me anymore? 3, because everybody needs 3. Everybody have to have 3 generalized coordinates. 3 generalized coordinates. So what are these generalized coordinates? That's translation of body reference. Translation of body reference coordinate system in X and Y direction and angle theta. So I have 3 coordinates. And then I got the new player in the game. So there comes a new component that we have to start looking at. By the way, what is that we're missing here is a body reference coordinate system is not shown in the figure, but we can place that anywhere we want. It's not changing the story at all. But we got the new player. And the name of the new player is force, externally applied force. And this force is applying to one particular location. Let's say this particle is where the force is applying. And this force consists of two components. And these forces are force in global x direction and force component in a global y direction. Our challenge is this. Now we have two sets of coordinates. I have global coordinates, which is the one where the forces are expressed, and tennorized coordinates. And I have to find the relation between these two sets of coordinates. I have to find it because I have to find a way that automatically maps representation of forces from the global coordinate system to be expressed by using tennorized coordinates. And they're not the same. Originally, they're not the same. You can see that already. How you can see it? Based on the numbers. Because look at that. So this consists of two components. This consists of three components. So if the component number is not the same, so it's not working out. So I have to find this relationship. This is where the concept of virtual work comes into play. And don't think about it in a way that, how the virtual displacement look like, what is color it is and how small it is. Because typically it's explained that it is this very small displacement. Don't think about it that. Think about it as a tool that is necessary to have in order to introduce this mapping. And again, why we need this mapping? We have to have this mapping because the unknowns are everything for us. We have to express all the forces using the unknowns in order to be able to solve these unknowns. And again, the unknowns are called tennorized coordinates. How you like the story so far? You can say something now. Is it like you're thinking like, oh my God, my head's gonna explode in any minute now? Or what is that you're thinking?
So mapping of generalized coordinates in global coordinates?
Yeah, well, other way around, but exactly this. Because, look, force here is having two components, is expressed by using global coordinates. That's not good. I don't want to accept that because there is a big problem in that force. And the force problem is that it's not expressed by using tennorized coordinates. What are the tennorized coordinates? Here it is. This is tennorized coordinates. That's what I have to do because remember what I'm solving here is the tennorized coordinates. That's what I'm doing. Okay, because here's the story. I mentioned this that I'm using this Newton's equation that is a mass multiplied by acceleration. So this is supposed to be r dot dot. It's going to be very hard to use this equation to solve the unknowns, which are hidden inside of the forces, and the unknowns are a vector of tennorized coordinates. Here too, they are hidden to these expressions, so they are not explicitly mentioned. Now I would like them to be explicitly mentioned. That's why I would like to express the forces by using tennorized coordinates. I know that this is a bit hard and I'm slow and you would like to go ahead, but still I would like you to think about this a bit. Now, so how it goes then in details. So the big picture was as I explained. So let's move a little bit about the details. And now the details is as follows. So we can introduce the virtual displacement, which is kind of like a displacement. The difference is that when the virtual displacement takes place, we are assuming time is not running. So that's the big difference between the displacement and virtual displacement. And of course, we are saying that the virtual displacement is very small and this and that. That's less significant. But what is significant is that we are doing the displacement such the way that time is assumed to be frozen. How you can make that happen in reality? You can't. Because how you can move this here to here without time is not running. That's why this is mathematical concept. Mathematical concept, what we need in order to have that necessary mapping between the global coordinate system and generalized coordinates. Okay, but with help of virtual displacement, we can express something that is called virtual work. Virtual work is like a real work, except displacement is virtual displacement. That's a big difference. That's what we're going to use in order to express the dynamic equilibrium between externally applied forces and inertial forces. That's how it goes. Now, I'm not at all sure, like, what is that you're thinking? Are you thinking that, yes, this makes sense? That's what I've been always thinking about virtual displacement, or are you thinking that, oh my God, another 15 minutes and then I'm off, and never ever come back? Which one it is? Is it like never ever come back, or all this makes sense? I knew it already a long time ago.
In between.
Okay, it's here, somewhere between. Oh, well, I'm happy with that. I'm happy with that. So others, if it feels too easy, I can speed up a bit, because I know that I'm slow now, but I would like to think this concept. Why this is, by the way, because I knew that you have heard all these stories about virtual work and virtual displacement and this and that, but still, it's a concept that is very often misused. And it's very often misused because there's a certain condition that you have to fulfill in order to find the dynamic equilibrium. We're going to take a look at these conditions a bit later, but today we only worried about how to express the forces by using generalized coordinates. Okay, so now how it goes. The only way to really learn this is that we have to take a look at an example. So I have here, again, the beam-like body, and in my beam-like body I have externally applied force that is applying in a position that is called O. All right? So here is my force component, and force component here consists of two components, because this is a force that is expressed by using global coordinate system. So this force will have a projection along the global x and the global y coordinate axis. So it consists of two components. And what I really wanted to do is that I would like to express these forces in terms of generalized coordinates. It will be possible with help of virtual work, and what I need to do in the very beginning is that I need to express very exactly this force is applying in my system. Well, that's going to be very simple, because I'm going to simply use the kinematics that I'm very much familiar with. I'm going to first express translation of body reference coordinate system, then I'm going to take into account the body orientation, and finally, with help of vector g bar, I end up to be in a position where the force is applying. Okay, now, force multiplied by displacement, that's going to give me work. And that's what I'm going to take a look at next. And I'm going to use this special kind of work, because in conventional work, it's all about, force multiplied by displacement in the direction of force. How you can express that using the kinematics that we are very much familiar with? Well, displacement in the direction of force can be expressed in such the way that you have original point where the force is applying and point where that is moving because of the force applying on it. All right, so that's the difference. That is called delta R. And this delta R you can compute by simply taking two vectors of R and taking its difference. Okay, makes sense. Now, delta R can be written as it is shown here. Now, if you take your mathematic handbook and you compute the delta R, you can express in such the way that you can take first partial R, partial t here of course is time, multiplied by delta t, and this is where the time is running, because I have a difference in time, and then I have here partial R, partial q multiplied by delta q. Now, in case of virtual work, I don't care about time. I'm assuming time to be not running, delta t is equal to 0 because time is not running. So I'm going to ignore this component like it is doing here. I'm ignoring it. So in the case of virtual work, I have this virtual displacement multiplied by force. And now when I'm using the mathematics, I can express this delta r such the way that is partial r partial q multiplied by delta q. I know this is painful, and you hear me like partial this, partial delta this, very unclear, so this is big mess. But we got something very surprising here, because when you take a close look about this, I have here partial r, partial q. This will be the mapping matrix that we desperately need in order to change the point of view and in order to convert force from global coordinate system to be expressed by using generalized coordinates. So this guy here is a mapping matrix. Matrix because R is a vector of 2 components, Q is a vector of 3 components. So it's going to give me vector where there will be 2 rows, 3 columns. And that's exactly what is doing the mapping that I'm looking at. All right. So let's take a look. So let's take a look how this goes. So I have here virtual displacement, virtual work done by this externally applied force. Okay? So how it goes, I have force multiplied by displacement. This time, virtual displacement. A virtual displacement is a displacement where the time is not running when the displacement takes a place. All right? Force multiplied by displacement. How can I express the details of that displacement? R can be expressed like so in here. How can I express that? I can simply using the mathematics, and express the relation between the delta R and delta Q. This is global coordinate system. This is generalized coordinate system. Can you see that difference? Something that is relating these two things is this mapping, which you can get by doing that partial operation. And you do not need to be afraid of partial operation because we already did that in case of Jacobian matrix. Remember the Jacobian matrix was all about the partial operations. It was a partial operation of constraints with respect to generalized coordinates. Now the only difference is that instead of using constraints here, we're using the position where the force is applying. That's it. You've never been this quiet before. So if there's something wrong, no, nothing wrong. So you're just focusing on this, right? Okay, so let's go ahead. Okay, let's have to do the details of this position to that previous equation. And then I'm going to take this partial operation. So I'm going to take a partial of this operation, partial of this vector with respect to my generalized coordinates. You will see what happened. First, you're going to differentiate this with respect to Rx. You're going to get 1. And then with the Ry, you're going to get 0. And then others are expressed here. The same thing with the x component of vector r, and then this is how it looks. And now when I'm using certain kind of notations here, special notations, and the notations go such the way that part of this mapping matrix can be called as a rotation matrix that is differentiated with respect to angle theta, multiplied by vector u bar. U bar is telling where the force is applying. What I have here as a submatrix is a 2x2 identity matrix. An identity matrix, let's take a look at the details, is this part. So it's a 2x2 matrix where the diagonal component will be equal to 1, off diagonal component will be equal to 0. Okay, now when I'm putting everything together, this is the big picture. This is how it looks. I will get started. I don't know where to get started here, but so maybe the best way to get started is that we have the concept of virtual work. Virtual work is a force multiplied by displacement. This time we're going to deal with the virtual displacement, and because we're dealing with the virtual displacement, this delta R can be expressed as it is shown here. So delta R and delta Q will be related. They will be related. So two different coordinate systems will be coming together. They will have a connection, and that connection is mathematically expressed by this mapping matrix that is converting things from global coordinate system to be expressed by using tenorized coordinates. Now, how is the details of this mapping matrix? That can be written as it is shown here. Okay. So let's take an even bigger picture than that. Let's take a look what it means in terms of forces. I have here virtual work done by external applied force, and that force is the one that is expressed by using global coordinate system. Now I'm going to use this mapping matrix. Once I multiply the force with the mapping matrix, I will have a force that consists of three components. And this force is now expressed by using tenorized coordinates. That's why this vector here will be called as a tenorized, as a vector of tenorized externally applied forces, as a tenorized externally applied forces. Tenorized comes from the fact that we are using tenorized coordinates to express that externally applied force. I know this is painful. We need to take a look at an example. And, this is a summary, but let's skip that. Let's look one example. This is kind of necessary to look because otherwise you will be so confused that there is no limit. So let's look. And I know that it's about time to close. So this is a final thing. So I have here beam-like body. In the beam-like body, I have a simple force that is applying in the system. And that force is a gravity force. Gravity force you can get by taking the mass of the body multiplied by a gravity constant. And it's applying in a minus y direction. And again, this force is expressed by using global coordinate system. That's why it consists of two components. Clear? Now, what I really wanted to do is that I would like to express these forces by using tenorized coordinates. Tenorized coordinates for this system, because it consists of one body, is Rx, Ry, and angle theta. Clear? Okay, let's make it happen. So let's do this all the way. So let's first express where the force is applying, where is its location. So here is where the force is applying. And all the difficult component here is that I kind of, I create this partial R, partial Q already such the way that I'm using this automated expression. So this is already like, the expression that is very sophisticated. No really need to do this partial operation. But as a result of the partial operation, that is what is coming out. And all I think that I needed here is that I need to express this vector U bar, where the force is applying with respect to body reference coordinate system. Let's take a look. So we have here body reference coordinate system that is applying here, and the vector U bar is the one that is traveling along the the body reference coordinate x direction to this point. And if the length of the body is L, then the vector U bar have to be L divided by 2, 0. You see that? Okay? That's the information you need to substitute here. So it's L divided by 2, 0. And then you put this one here, here. And then you have this mapping matrix. And now when you have the mapping matrix, you multiply the force with the mapping matrix. What is it you're going to get? You're going to get forces that are expressed by using tenorized coordinates. How it reads. So Rx component will be equal to 0. Ry component will be exactly same that in the case of global. Well, this force is expressed using global coordinate system. And then this is what is that the body reference coordinate system is experiencing as a moment that is imposing to coordinate theta. That's how it goes. Well, remember a few weeks back, I said that this is going to be, there was this curve about time and level of difficulty, LV. And I promised that it's going to be painful. So what do you think? Next week is the more painful.
You have to explain this one more.
Yeah, but the next week is going to be, because this is easy to deal with. What we're going to do next, well, not next week, sometimes next week, is that we have to take a look. What is that we can do with inertia forces? Oh boy, that's a painful story. But, we will be together, so we can hold a hand and we can breathe deeply, so we can make this happen. So once we can, and remember, these are the only really difficult thing. After that, everything is downhill. Just enjoying life. That's what's going to happen. So one more rocky road and then we're done. I can guarantee you that.
Then comes exam.
Yeah, then comes exam. Which is really the rocky road. That's the real challenge then. But you would like me to repeat this next Monday. Sure, I'm repeating this so many times that you are finally saying that, Aki, please stop. I know this back and forth already, so stop now. But that's what's going to happen. Like remember, in dynamics we have externally applied forces and inertia forces. And look what we can do. According to D'Alembert's rule, this is very important. D'Alembert was able to express this equation such the way that he wrote this equation like F minus and became world famous. But there was something else than just that. Because we can all do it. We can all take everything to left-hand side of the equation, and we are not becoming world famous because of that. But he figured out something that is more important than just put them in a left-hand side of the equation. He figured out that inertia forces can be treated exactly same way than externally applied forces. So here it is. So we can apply this concept to inertia forces. Because look, this too is expressed by using global coordinates. How you know that? Because the vector r dot dot consists of two components, and these components are acceleration along the global x and y coordinate axis. So no good for us. We have no use for forces like that. I mean, that we have the use, but first we have to convert them to be expressed by using tenorized coordinates. Okay, so then how is that I can make you smiling again? Is it like no way back? Your life is completely ruined. Nothing left. So it was a beautiful life, happy life, and then you came to this lecture, all gone. Nothing left. What is that I can do for you? Nothing. Is it like done deal? Okay, what if I promise you this? Let me cut the corners such the way that I really wanted to explain the kind of the physical interpretation behind all this. And then we're gonna look, how is it you can train yourself to be Superman and Superwoman in that exam, written exam. Okay? How it sounds. Okay, before we are going, let me show you the in-class quiz that I'm about to ask on Monday. What is the physical interpretation of that matrix?
C, yes.
What do you think? Would you like to answer this already today, or you want to have some time to think about it? Should we try it today?
Yes.
Okay, so let me put it on, because maybe miracle will happen. You never know. Next.
We get 2 chances for this today and then next one.
Yeah, that's right. I make my promise. So, yeah, that's a good one. That's a really good one, because let's take a look what is that you're thinking this week, and if there's any improvements next Monday. It's really going to make me feel sad if we're going to go, from today's score to lower one. This will be very, very unfortunate. But we'll see. So the question is this. Physical interpretation of matrix, which is a partial R, partial Q. Now, think about if you would jump into this streaming, you would have absolutely no idea what is that we're discussing. That's why it is critical to follow these lectures every week, because you skip 1 week, you're coming back and you're like, oh my God, this is from another planet. And it's not. It's just that we are proceeding with the good speed. Okay, so question is, again, let me explain what are the options. Defines the relationship between the global coordinates and constraints. Defines the relationship between the constraints and generalized coordinates. So the first 2 options is related to constraints. Then defines the relationship between the global and generalized coordinates, and defines the relationship between external applied forces and constraints. So all except one are related to constraints. So is this about the constraints or not? What? Yes, but no. How could that gonna help me? So it's not gonna help. Yes, but no. So it's a yes or no? You say it. Okay, so let's take a look. No, where is that we are now? So can you please enter your answer, and then we're gonna close for today? Oh, it's already 6 o'clock.
If we trust your words, you said many times during the lecture. That was
Yeah, you should trust my word. What I'm saying is absolutely true. I've been in this business already like more than 25 years.
teaching.
No, as a, I got my way more than 25 years. I got my doctor degree already 22 years ago. Think about that. So that makes me what? 110 years old.
Yeah, you look young.
Yeah, but still I am like 110 years old. Yeah, think about that.
What age did you get your doctoral degree?
So what is a usual age?
What was your age when you got your...
I'm not going to tell you that, so you need to guess that. Okay, so are we done? Oh, so we have 80. So what would you like to see this? So 100%. That would be really awesome. If 100%, we need to figure out how is that we can celebrate that if it's going to be 100%. Is there going to be celebration of some kind?
Still 96.
So we go and drink a lot of alcohol, the Finnish way, no?
Yes.
Ready? Okay?
Still
63. 63. Okay, keep this number, put this number in your mind. We will get back to this next Monday, and if it is lower than 63, we can stop having lectures, because obviously it makes you just more confused. All right, thank you very much, and see you on Monday then.